Hi, everyone. We are jumping into our next set of sections. We'll call it Chapter 4, Applications of Derivatives. Turns out we start with a couple of sections from Chapter 3, but keeping with the theme of applications, I find those fit much better grouped along with these other sections from Chapter 4. So we'll start with related rates. Then we'll move to linear approximations and differentials. Then we'll get into Chapter 4 in the actual book, 4.1, maximum and minimum values, and 4.3, shapes of graphs. Those go together really well, so I put them back to back. All of that is actually talking about graphs of functions and what we can learn about graphs using derivatives. Then we'll do 4.2, the mean value theorem. Another good application in 4.7, optimization, Newton's method, and finally in 4.9, we'll learn about antiderivatives. Okay, 3.9, related rates. This is a big one, and we can argue we've done applications of derivatives in previous sections. Those were not on the same level as what we're going to see with these applications, right? A clear distinction between them. Okay, starting off strong with related rates. What's going on here with related rates? Turns out this is an application of implicit differentiation. So we're going to start off just with an example, kind of get ourselves refamiliar with implicit differentiation, and we're even going to think about it a little bit differently. We're going to think about implicit differentiation of x and y with respect to a new variable t. Okay, so let's use our example x squared plus y squared equals 25. This time, we're going to take the derivative of both sides with respect to t. Here, we're thinking of our independent variable as t, and our two dependent variables, x and y. So think of x as being a function of t and y as being a function of t. And here we go, taking the derivative of both sides with respect to t would look like this. D over dt applied to x squared plus y squared equals d over dt of 25. Now, if both x and y are functions of t, how is this derivative of the left side going to work out? Well, both of them now are implicit because our third variable is different than the other two. So when we take the derivative of x squared, it's going to look like 2x times dx over dt. And when we take the derivative of y squared, it's going to look like 2y dy over dt. And of course, on the right side, the derivative of 25, no matter what the variable is going to be 0. So there you go, a little bit of practice doing implicit differentiation with respect to a third variable t. Now, where do we get the name related rates? We can actually see it right there in that last line. We can see how the two rates, dx over dt and dy over dt, are related to one another. Remember, these are the derivatives of x and the derivative of y. That's the rate of change of x with respect to t and the rate of change of y with respect to t. And because they're connected in this equation, we can see how this rate of change is related to this other rate of change, hence the name related rates. Okay. They are literally the related rates. All right, best thing to do at this point, just jump right into an example, dive in, see how this all works. So we'll start with this. A 72-inch ladder is leaning against a house. The base of the ladder is 36 inches from the house and slides away at 5 inches per second. So you got this ladder leaning up against a wall of your house, right? And then the base, the bottom of the ladder starts to slide out. And as it does that, right, the top of the ladder like slips down the wall straight to the ground. So how fast is the top of the ladder sliding down the house, right, at that same moment? And okay, we'll round, we'll include units. Sounds good. Let's jump over here. Let me try and summarize again. We got a 72-inch ladder against a house. The base slides away. Oh, a little ahead of myself. The base is 36 inches from the house, and it slides away at 5 inches per second. So the question is, how fast is the top of the ladder sliding down the wall? All right, what we're going to do in a situation like this, we're going to draw a picture. We're going to start labeling things. So I'm going to draw this house, right? Something like that, just real simple. There's the wall, here's the ground, right? Here's the ladder leaning up against the wall. And we know that ladder is 72 inches. Let's go do that. Also, let's see, this forms a right triangle. Okay. Let's see. Here's what's happening. The base of the ladder is sliding out this way. As it does, the top of the ladder slides down. So think about the distance from the wall to the base of that ladder, right? That is, since the ladder is in motion, this distance here is changing. Because this distance is changing, we need to label it with a variable, which can also change. So we're going to call this distance along the bottom x, because it is the ladder's in motion. So that distance from the wall to the base is changing. It's getting longer. At the same time, this distance along the wall to the very top of the ladder, that distance changes, right? Because the ladder starts to slide down. So we need to label that with the variable. Let's call it y. Let me make a note here. Variables represent quantities that are changing. Now, notice they also told us that the base is 36 inches from the house, right? So it might be tempting to label that with a number. Don't do it. This distance is in motion, right? If we label something with a number, then we're saying it's always that length. That is true of the ladder. The ladder is always 72 inches, but this distance here is not always the 36, okay? Now, in the end, we are going to use the fact that we're looking at the moment when the ladder is 36 inches away, but it's like it's passing through that value. And we kind of like take a freeze frame right at that instant and kind of look at what's happening while it's in motion. But for now, we got to label it with a variable. Okay, they also tell us that the base is sliding away at 5 inches per second. We could label that arrow with the 5, you know, if we wanted. That makes sense. Okay, here's what we want to do. Based on our picture, we want to come up with an equation that connects x and y. Is there an equation that we know, some kind of formula maybe, that would connect x and y together in that equation? We'd say, hey, you know what? I'm looking at a right triangle. Pythagorean theorem, right? X squared plus y squared would equal 72 squared. Perfect. Now you might think, hey, we should actually square the 72. Turns out we don't need to. Why? Because now that we have an equation, we're going to take the derivative of both sides with respect to t. Right. So when we do that, derivative here with respect to t, 2x dx over dt plus 2y dy over dt equals, this is a number, derivative is 0. Okay, we're doing really, really good. Now you might think, all right, we got this derivative equation now. What is that telling us about this situation? All right. X and Y would represent the lengths at any given moment. So if we wanted to figure out what's happening at the exact moment when the base is 36 inches away, we could plug in the 36 there. The Y, right? We need to know the Y value at that same moment. And we need to say, okay, what are the rates of change going on? So it turns out one of these rates of change is what we're trying to figure out. What is the question asking? How fast is the top of the ladder sliding down the house? Well, which rate, dx over dt, or is it dy over dt, that would connect with this question? How fast is the top of the ladder sliding down? We see, well, the way we labeled it, as the ladder slides down, that's changing y. So the dy over dt describes how fast the top of the ladder slides down. The dx over dt tells us how fast the bottom of the ladder, the base of the ladder, is sliding out. Well, this is great. They tell us that value, right? It was 5 inches per second. We know x, the moment in question, is 36. Let's kind of put these out. X will be 36. Dx over dt will be 5 inches per second. Oh, you know what though? So we can plug in values for x, we can plug in 5, but we don't know what y is going to equal. They didn't tell us that. Does that mean we're stuck? No. Here's what we can do. Since we know x, we can go back to the original equation here, plug x in, and figure out y at the same moment. Use x equals 36 and the original equation before we took a derivative. So we know 36 squared plus y squared equals 72 squared. What does that tell us for y? Let's see. 72 squared minus 36 squared, and then we'll take a square root. It's square root 3888. That'll be good. I'll keep that for now. Prefer not to round it until the very end of the question. All right, awesome. I know x, I know dx over dt, I know y. We can plug all of those in, and we can solve for dy over dt. We'll have it. Let me write this out again. 2x dx over dt plus 2y dy over dt equals 0. So that's 2 times 36 times 5 plus 2 times square root 3888 times dy over dt. Solving for dy over dt. Let's see, what would we do? Subtract this number, divide by this number, -2 times 36 times 5 over 2 times square root 3888. And now let's get this. I think we were supposed to round to 2 decimal places. Let's do that. -2 times 36 times 5 divided by 2 square root 3888. And I ended up with, when I round, -2.89 for dy over dt. What are the units there? Think about the units of y and the units of t. T, we use the letter T because it represents time. So let's see, back here, y, all of our measurements were in inches. So our y, our length there is going to be inches per second in this case. There we go. Notice that our final answer is negative. Does that make sense that dy over dt would end up being negative? It does. If you think about that original drawing, since the top is sliding down, that value of y is shrinking. So we'd say the rate of change is negative because y is getting smaller. So it actually makes a lot of sense that it came out to be negative. The x, on the other hand, the x value is getting bigger. So dx over dt was +5. That makes sense too. Okay, very nice. Let's stop here. More examples in the next one.